Hello, everybody. Welcome to July 14th class meeting, second day of second semester. We're going to get into chapter 14 stuff, which is all gas laws. Before we do that, though, we're going to talk a little bit about phase diagrams because I forgot to do that last time. So we'll talk about that real quick. Won't take long. And then that'll be the end of this unit, Unit 5 for the class. First unit of second semester. Your exam will be tomorrow then, 7:15. It's only 30 questions. I tried to make it pretty simple. Only a tiny amount of calculator work, but that'll be up. I mean, it's up right now, but you'll be able to see it tomorrow morning at 8 a.m. So let's get right into phase diagrams, which, again, I forgot to talk about yesterday. So I'm not going to attempt to draw them because I'm a terrible artist. So you may have seen this in your reading or what have you. And I'm going to do this. We're going to take a screenshot so we can zoom up. Because Google Images doesn't like me to zoom up anymore. All right, so what we have here is we have a graph of pressure versus temperature. And one of the things that we're going to talk about today is when we're talking about a gas, we're going to talk about its pressure and its temperature. And we said that it was very important to talk about pressure for gases because of the fact that when you pressurize a gas, because a gas is compressible, you can have the space change in between the gases, so the volume can change and all that. So what's also important for, what pressure is also important for, and temperature, is phase change in a substance. So when we talk about Earth, we usually say, room temperature or standard conditions. And what that means is that we have a phase diagram. So how something changes phases through the temperature increase compared to pressure. So for instance, if we think about water, water is a solid at 32 degrees C. And then if you start to heat it up, say like, 32 degrees. And if you start to heat it up, it will start to eventually become a gas. So what we have here is basically the solid, and we have the liquid, and we have the gas phase. And then over here, we have what's called supercritical, which is when things start to behave very, very weirdly. So if we looked at water, for instance, if we were at 30 degrees, I'm using Fahrenheit here. If we were at 0 degrees Celsius and 1 atmosphere, so like say this is 1 atm down here. If we go like this, you'll notice that at 0 degrees, we're going to transition from the solid to the liquid phase. But if we increase the pressure a little bit, say we go to 2 atm, you'll notice that at 0 degrees, we're going to stay a solid. And it's when we finally get to another temperature, I don't really know what it is off this scale, then you'll notice that we're going to go into the gas phase first, which is what's going to cause what's called sublimation. And so pressure has an effect on phase changes. So basically, all I want you to know about phase diagrams is they show how something transitions between its different phases. And this is a good example of the phase diagram for water. You can see that we have kind of a negative slope on this transition here. Sometimes they get kind of ugly, but you can see this one right here has a negative slope on the transition phase right here, and then we have a positive slope, and that is going to be caused by the interactions between the molecules, the intermolecular forces. So a typical solubility curve is like the one I'm showing you up here, and what it shows you is how it transitions. And what you'll notice is that obviously as you just increase temperature, things go solid to liquid to gas. That's it. And then if you get their temperature really crazy, then they will go into supercritical. However, because of pressure, if you stick those molecules next to each other because you're pushing on them, that increases the amount of those intermolecular forces, and therefore you get the phases to stick around for longer than they would. You'll notice right down here, if we have like 0 ATM down here, and we're looking at water, we're just going to be able to switch very quickly through that. And temperature-wise, it's going to heat up very quickly. So some key points right here. This is what's called the triple point. It's the pressure and temperature point when all three phases of matter exist at one time. So if you've ever been driving and you've seen a lake in the cold weather or the winter time, you might see it and have it look like it's frozen, but you can see water and it looks like steam's coming off of it. And that's because you've hit the triple point of water, where the vapor pressure and the solid and the liquid phases are all existing at once. And then you have here what's called the critical point, and that's when you start to reach the limit of the molecular structure of the particular substance you're dealing with. For instance, carbon dioxide, CO2, is really cool in that at low pressures, it will sublime. It will go from the solid phase into the gas phase. But at higher pressures, you can get it to become liquid carbon dioxide. But what's really cool is after the critical point, it becomes a supercritical fluid. And what that means is if you were to look at carbon dioxide in this supercritical state, it would not look like a fluid. It would look like a gas, but you could see it moving in a fluid direction. It would have convection currents and all these cool, interesting things. So supercritical fluid is a very interesting way of doing things. There are a couple different ways to use supercritical carbon dioxide for different cool things. One of the things they use it for is for like the extraction of like caffeine or other non-liquid soluble, or sorry, water soluble substances out of things, which is pretty cool. You can also use it for making aerogel and things like that. So that's a phase diagram. You really just need to know that it shows the three phases. Triple point is where all three of them exist at once, and then the critical point is when everything just kind of breaks down. So that's all I really wanted to say about that. I meant to say that yesterday, but I forgot, because it was like a 3-minute discussion. All right. So let's get into then the gas laws. Okay, so when it came to gases were one of the first things that we decided to study back in the 1600s when we first started doing science. And one of the big questions they had were looking at like the behavior of gases. So one of the big famous people is a guy named Boyle, and what he was interested in was pressure. So what he did is he created a bunch of these cylinder chambers where he could put weights on here. The weights would look like this back in the day. And he could add weights to that, and he would have a sample of gas in here, say, it was just air probably at the time. And what he would notice is that when he would increase the weight, so therefore if he would increase the pressure, obviously if you add weights to this, what is it going to do? It's going to drive this plunger down, right? And so what Boyle was interested in was these ratios of this change. So the pressure would go up, the volume would go down. And this relationship he called an indirect relationship, which means that if one goes up, the other goes down. So if you have ever played with like a shock absorber, you'll notice that when you press in on the shock absorber, it increases the pressure and it wants to push back out. It's like a big old spring. So what Boyle was interested in was looking at what is actually happening here. Is this some weird ratio, or is it pretty simple? Like if the volume was 2 and I made the volume down to 1, what happened to the mass and therefore the pressure? Did I have to, sorry, that's a gram. Did my 1 gram become 2 grams, or did it become 8 grams? And so what is the relationship? And so that was what kind of drove the discovery of all of the gas laws, was asking ourselves, okay, liquids and solids have these cool properties where they have density and they have volume, but they don't, they don't care if you pressurize them. They don't really care too much. If you heat them up, they expand and contract, but not very much. Gases, though, temperature greatly affects them, changes the pressure quite a bit, changes the volume quite a bit, and then, of course, amounts of gas change everything. So what the gas laws are all about, describing a gas. And because the way we need to describe a gas is in terms of pressure, temperature, volume, and finally amount of gas, which we measure in N, which is a terrible N. So let's draw a better N. So what the gas laws do are saying, okay, well, instead of when we talk about a solid, we can just simply state its mass or its density, and that pretty much describes all we need to know about it. But when it comes to a gas, we need to describe all of these things if we really want to understand all of what's going on with that gas. So the gas laws are ways to describe like what will happen to the gas if you affect any of these particular conditions that the gas has. So our first example, like I said, one of the fathers of the scientific method is Boyle. And what Boyle's law says, as we just stated, was relating pressure and volume together. And what Boyle said was that they are what we call indirect. What does that mean? That means if the pressure goes up, the volume goes down and vice versa. But the reason why Boyle gets to name himself after this is because, one, he basically invented the scientific method to prove this. But what he proved is that it was the same ratio. So what do I mean by that? Well, say we had a pressure originally equaling 1 atmosphere, and we had a volume originally equaling 4 liters. Well, if we were to shift that pressure to 2 atmospheres, what he noticed is that the volume would go down by that same ratio. So if we doubled the pressure, we would half the volume, 2 liters. And so what we have here is what's called an indirect relationship. And Boyle mathematically shows this relationship in a simple multiplication equality, where if we set these two situations equal to each other, for them to maintain their equality, one will have to go up, the other one will have to go down by that same ratio. And Boyle basically invents the scientific method to prove this really cool, interesting characteristic. Now, he, obviously is talking about it in terms of a constant, saying like all pressure volumes will have a constant, and that constant will be the ratio that they change. But for our purposes, this is what we're going to write as Boyle's law, an indirect relationship where these things are changing. But notice that it didn't affect the amount of gas or the temperature. So this only was occurring if we made sure that we had constant temperature and constant amount. Keep wanting to say volume. So not too hard to keep things constant amount. You can just do this in a jar or do this in his little plunger experiments that he had. Okay. So that is Boyle's law. That's what he discovered. So you can see that. So then there is a famous nobleman, and he is super interested in hot air balloons. And he's friends with a guy named Boyle, and his name is Charles. And what Charles is super interested in is he's wondering, why do hot air balloons go up? Right? It's really interesting to him that the balloon, before you heat it up, so the temperature goes up, the volume inside the balloon goes up. But then that also makes your balloon float. And he really wants to know why this is. He wants to understand the relationship between volume and temperature. So he gets together with Boyle because he's not the best scientist. He's really just a nobleman with lots of money and time. And he gets together and he wants to start doing experiments. But because he's in a different part of the world, they decide that they need to set up what's called a standard. And so basically they're going to compare all gases together, and they're going to compare them first at what's called STP, so standard temperature and pressure. And what standard temperature and pressure is bringing all gases to 0 degrees C, so basically freezing point, and 1 atmosphere. And remember from last week that we have equivalences for all of our pressures. So STP is 0 degrees C, but 1 ATM, but it could also be 760 mmHg, or it could be 101.3 kPa. That's all the same thing. Remember that. So this establishes this idea of what's called STP. So if you ever hear in a gas law, they're talking about standard conditions, or they're talking about standard temperature and pressure, that's what they're talking about. And that was just kind of their baseline. And the reason why they did this was because a lot of the times when you were doing an experiment on gases, like say for instance Charles here, he was going to go outside. And so if he's going outside, regulating the pressure is going to be difficult because the pressure is going to change. And so we had to kind of have a baseline, like what is going to be our starting point? And so that's what STP was established for. Now, why 0 degrees C? Well, if you have ice, you can bring things to 0 degrees C very easily. But the more important thing is water. At 0 degrees C, water will turn from a vapor in the air into a liquid and eventually begin to freeze. So you can get rid of a lot of the water vapor in the air if you start your gas at 0 degrees C. This will cause the water to condense, and then that way you can take it kind of out of your equations. So that's STP. So Charles is super interested in hot air balloons. He wants to know about hot air balloons, and he wants to know why they float. Why does getting a balloon hot float? So buoyancy is Archimedes, and buoyancy basically says, if you're going to be buoyant, you're going to be looking at density differences. So if the density is less than the density of the thing around it, then this will float. Well, let's rewrite density. Density is mass over volume. So if the mass 1 and the volume 1 is less than the mass 2 and volume 2, then that means that whatever's going on here will float. Well, in a hot air balloon, you weren't changing the mass, so the mass was staying the same. So it must be this volume change that was causing the balloons to float, to go up in the air. And so what Charles wanted to know was, okay, well then how hot do I really need to get my balloon to cause enough volume change to get it to go up? And is that volume change, just like in the fact of, in the Boyle's case, is it going to be that same ratio of change where if I double the temperature, I'll double the volume? So Charles starts doing his experiments. And he has a problem. He finds that, yes, it's a direct relationship, but he's finding that it's not a perfect ratio. So for instance, he does his experiment and say his volume 1 starts off at 10 liters and his temperature starts off at 25 degrees C. Well, when he then changes this situation to 50 degrees C, which looks like a doubling of the temperature, he would notice a very, very small volume change. Now, that's exaggerated just for the sake of numbers. It'd probably only be 11, to be honest with you. Be less than that. He noticed that it basically, even though it looked like he doubled the temperature, the volume barely changed. So then he goes, okay, well, let's do this. Well, instead of doubling the temperature, let's find out at what temperature does the actual volume double. So let's just keep heating this up until we get it to change to 20 liters, and let's measure the temperature. And when he does that, he finds out that this thing doubles to almost 500 degrees C. And he's like, well, wait a minute, that's weird. What's going on here? So again, Charles, because he's friends with Boyle, he does the scientific method and he does a ton of observations. And what he finds is, not Charles, but Boyle and eventually a guy named Kelvin, is that the temperature scale is wrong. Celsius is designed around setting 0 to water freezing and 100 to water boiling. So we'll say boiling point, and this is freezing point. Well, the problem that Kelvin has is that Kelvin says, well, there's plenty of liquids that don't freeze at 0 and they don't boil at 100. They might boil sooner and they might freeze sooner or later. And there must be some basement, some bottom number, which is the lowest absolute temperature. And that what Charles is probably seeing, the reason why he's not seeing the cool direct or indirect relationship ratio that Boyle was seeing, is because our temperature scale must be wrong. The universe has way more stuff in it besides water. So what Kelvin does is Kelvin redefines temperature. Kelvin redefines temperature as average kinetic energy. So Ke is kinetic energy. So if you're looking at the temperature of something, what you're actually looking at is the average kinetic energy for all of that system. And so what Kelvin does is he resets the Celsius scale. He doesn't change the increments between it, but he goes ahead and he calls that basement absolute 0, which is just 0 K. Not 0 degrees K, just 0K. And so when he does this, he finds that water is actually freezing at 273K, meaning water boiling is at 373K. So when you used this, when you used the Kelvin scale, you then saw the direct relationship. So if you guys remember, degrees C plus 273 is the Kelvin scale. So when we adjust this to Kelvin, this becomes 298 Kelvin, which means that the temperature for this to cause this to boil is going to be 596 Kelvin. That is a doubling. And then, of course, subtract 273 from that to get the Celsius temperature. So that was what was happening with Charles's law. It was a direct relationship that was directly proportional, meaning one goes up, the other one goes down, one goes up, the other one goes up in a direct proportion, as long as the temperature scale was in Kelvin. So Kelvin has the added bonus of making the relationships directly proportional, but also there was another big important thing about this Kelvin scale. So say, for instance, we plugged in our numbers from our example earlier, and we said we had 10.0 liters, and we're at 25 degrees C. Well, that was going to equal what volume at 50 degrees C? Well, this is not a hard problem to do because this will give us some number. It's easy math. But what if we were starting off at negative 25 degrees C? Do you see what the problem is going to be? Our answer, volume 2, is going to be negative. And the problem that they had at the time, and the problem that we still have, is what does it mean to have negative volume? And the answer is we don't know, because a vacuum is 0 volume. What is negative volume? So this was impossible. So another benefit for Kelvin was to get rid of the negative numbers. So instead of negative 25 degrees C, we just have plus 273 Kelvin. That gives us what? 248 Kelvin. And so if we're heating that up now to 50 degrees C like we did before, well, that's going to be 323 Kelvin. You'll notice now we have no negative numbers, and so our volume will be positive. So when we're talking about Charles's law, it is a direct relationship between volume and temperature, meaning they both go up and they both go down at the same time, and that we have to use Kelvin. Pressure is constant, so we don't let the pressure change. The amount of gas is constant, so we don't let the amount change. And temperature has to be in Kelvin. Otherwise, the ratio doesn't work. So I call that the hot air balloon law. You can also call it Charles's law. Where basically, why do hot air balloons go up? Well, when you increase the temperature from the hot air balloon to say, maybe that it was a nice day outside, so maybe it was 300 Kelvin, and you start getting that hot air to be, close to like 600 Kelvin, because we're getting it really hot, we're going to make our volume of our gas go from, let's say our hot air balloon is like 10,000 liters. Well, that means we're going to go to 20,000 liters. But look what that's going to do to our density. our mass is going to stay the same. So we can just call that mass. But our original volume was 10,000 liters, and our new volume is 20,000 liters. So you notice our density is going to be cut in half. And because the density of the air inside the balloon is half of the density of the air outside the balloon can float. Pretty cool. This is what also drives most convection currents. If you're looking at your convection oven, the heater is down here where all the fire is, and then you have your rack. Well, what's happening is the heat is going up, and because it is lower density than the air inside, the hot air goes up, it then gets away from the cold source, loses some of its energy to the surrounding air, and begins to sink. And this is being caused by the convection current, which is what we call it, but it's being caused by the difference in density, which can be explained by Charles's law. So that's Charles's law. V1 over T1 equals V2 over T2. So then the guy comes along and he's like, all right, we know the relationship between pressure and volume. We know the relationship between temperature and volume. Well, then what's the relationship between pressure and temperature? And this is Gay-Lussac, or Gay-Lussac, how you say it. I think it's C-A, no, S-S? I always spell it wrong. Let's hold on. G-A-Y-L-U-C-C. What's wrong with that? Charles Law. S-S-A-C. All right, there we go. S-S-A-C. Law. And Gay-Lussac's law is relating pressure and temperature, and he found that they were a direct relationship, meaning they both go up together. And this was holding volume constant and holding the amount constant. He came up with the equation that the pressure of a system will increase with the temperature of the system and vice versa. And it was directly proportional as long as temperature was in Kelvin. So if we have a hot air balloon, for instance, and we start to heat up the air in there, the air is going to move around more and it's going to exert more pressure on the walls of the container. And so the pressure inside the balloon is going to be higher than the pressure outside the balloon. Charles was trying to explain the hot air balloon by just looking at volume and temperature, but you also need to describe it in terms of pressure, and we would need Gay-Lussac's law to do that. Now, what I like to call this is the explosion law, because basically what this says is that if you don't let the volume change or the amount change of something, eventually you're going to, the temperature increase is going to cause such a large pressure increase that eventually your container is going to fail. So if we go to our PhET simulations from yesterday, you can see this in the gas laws PhET simulation. If you increase the temperature too much, it will explode. Hopefully that one's used to be a flash one, so we'll see if it still works. Gas properties, gases intro. Let's see. They changed which one it is. Okay, so they call it gases intro now. Oh, there's no lid on there. But we'll try it. They used to have a nice one. There we go. Gas laws. This one's probably it. Yeah, see, because now we have a lid. So if we look at this, we can actually see all the different laws in action. So we have some amount of gas in here, and you'll notice that it is at a particular pressure. So our first gas law, Boyle's law, was looking at the relationship between pressure and volume. So if we took our volume here and we cut it in half, you'll notice our pressure doubles. And then if we take our pressure again and return it back to it, it goes back to it. But you'll notice that the temperature was held constant. And the amount of gas was being able to be held constant. Then, in the terms of Charles' law, we started to see that if you heat the gas up, the volume of the gas increases. And if you cool the gas down, the volume of the gas decreases. Now, if we keep the volume constant and we start heating this up, what do you notice is happening to the pressure? The pressure is going up. So eventually, if we keep heating this up, we're going to eventually cause the pressure inside of this container to be so large that the container itself will fail. So sometimes there it goes, blows the lid off the top. So this is why I call it the exploding bean can law, because if you took a can of beans and you put it on your stove and didn't open it and turn your stove on, eventually that can of beans is going to explode. Or if you take a soda and you leave it in a car, in a hot car in like the desert, eventually you're going to cause that soda to explode, because the larger temperature increase causes the pressure to increase, and eventually you get the explosion. So those are all breaking down the individual relationships between pressure, temperature, and volume. But in a real world system, like I said, with, like a hot air balloon, really what's happening is not just two things are changing. All three of these things are changing at once. So we get what's called the combined gas law, where we put all of these laws together in the combined gas law. So we can look at, if the pressure was to increase, then that would cause a change in the volume, but it would also cause a change in the temperature. And this equation allows us to see how these different ratios would affect each other into the final outcome. So if we go to our original situation where we had, 1 atmosphere and we were looking at 10 liters of a gas, and we were at 200, we'll just say 300 Kelvin, and we were like, okay, well, what's going to happen to the pressure if we go to 20 liters of gas and a temperature of 600 Kelvin? Well, now we can plug in our numbers here. 1 ATM, we have 10.0 liters, and we have 300 Kelvin. Well, what is the new pressure then if the volume then changes to 20 liters, but the temperature is increased to 600 Kelvin? So now we can solve for pressure 2. We can put the 600 right here, and we can put the 20 down here. And these will cancel out because we switched them. And so now we can solve for this problem. Liters will cancel, Kelvin will cancel, and our answer is basically 10 times 600 divided by 600. And so that's what's going to happen to our pressure. Give me the calculator. And yeah, there we go. So 10, how many calculators you want to give me? 10 times 600. And then divide that by 600, we get 10. So our new pressure is going to be 10 ATM. Now, why does this make sense? Well, remember, pressure volume have an indirect relationship. The volume increased, so the pressure should decrease. But the temperature increased, so that makes the pressure increase. So because we had a doubling of the temperature and a doubling of the pressure, those two worked against each other. So instead of us seeing a doubling of the pressure and then a halving of the pressure, we see this come out. Oh, not 600, 60. I'm so dumb. 300 times 20 is 6,000. Yeah, I'm so stupid. So it's 1. I apologize. So you can notice that because this doubled and this doubled, and because one is direct and one is indirect, they canceled each other and the pressure didn't change. So that's what I was trying to show with that stupid example, but I'm not very dumb and dyslexic. There we go. I am very dumb and dyslexic. See, I just did it. My apologies. All right. So that's what's called the combined gas law. Pretty simple. So then what about amount? What's going on with amount? Well, we already talked about amount with that guy, Avogadro. If you guys remember, Avogadro said that 1 mole of any gas is 22.4 liters. But we said at STP. And you remember that STP is equal to 0 degrees C and 1 ATM, otherwise known as 101.3 kPa. So what Avogadro actually did, though, is he looked at volume and he looked at amount, and he noticed that they were a direct relationship, just like Gay-Lussac's law and Charles's law. And what he said, though, was that they all shared this phenomenon, that 22.4 liters was over 1 mole. So if you wanted to know the volume of something, you could just simply measure the amount of something. And then it was through his work that he was able to configure how the mole equaled grams using that molar mass. So Avogadro's work with gases is what led us to understanding the link between subatomic particles and mass. But really what he was just interested in was, if you take a balloon and you don't blow it up, its volume is lower than if you actually put air in it. So N1 to N2, because this was going up, well, then the volume had to go up. He was just interested in the specific ratio. And just asking yourself that question, if I double the amount of gas, does that double the volume? Led us to that 6.02 times 10 to the 23rd number. Pretty cool. But it also led us to the big discovery that all gases kind of behave the same way, in that they will all double, or they will all triple, or they will all be cut in half, or what have you. It didn't matter what type of gas it was. It only mattered what temperature, pressure, volume, and amount was going on. So again, when we're talking about practical situations, and then you guys can use that in calculations, you can just use, if you see STP, you can just use the conversion factor from the previous unit, where 1 mole is 22.4 liters, or vice versa, which is 22.4 liters is 1 mole. So if you're ever having a question where it says, you know, the volume of a gas was 50 liters, but is now only 25 liters, well, how much of the gas was lost? Well, then you can just simply use this as a conversion factor. You don't have to do the actual conversion. So now we have a problem. So keeping stuff constant is kind of a pain in the butt. And most of the time, a lot of things change all at once. So what we needed to do was needed to make a completely combined law, which we call the ideal gas law. Well, what we're going to do is we're going to combine everybody's work together. computer's starting to lag. And so this big ugly mess would be a real pain in the butt to solve all the time, because we would be constantly having to measure before and after conditions. But there's a reason why it's called the ideal gas law. What is an ideal gas? Ideal gases are always gases, meaning they can't be compressed or condensed. Can't be condensed is a better way to say it. So, for instance, helium is an ideal gas. If you take helium and you try and condense it, it will stay a gas. So helium is a good example of an ideal gas. The reason why it's an ideal gas is it has no intermolecular forces. But if we compare that to water vapor will switch to water liquid at certain temperatures. It can be condensed. And so it can't exist at all gas conditions like helium can. However, because of the work of Avogadro and other scientists, if hypothetically water could behave like an ideal gas, its properties would be exactly the same as an ideal gas. And so rather than worrying about every single gas having special conditions for it, what the ideal gas law says is that, okay, all gases behave the same way. So rather than constantly trying to measure their condition before and then measure their condition after, let's just plug in the conditions for a gas at STP. So standard pressure is 1 atm. What is standard volume? Well, Avogadro said that at 1 atmosphere, the volume of a gas will be 22.4 liters, as long as you have 1 mole of it. And this occurs at standard temperature and pressure, which is 273 Kelvin. So now, instead of pressure 1, volume 1, amount 1, temperature 1 equals pressure 2, volume 2, amount 2, temperature 2, this condition is the same for all gases all the time. And because this number doesn't change, it is a constant. And they gave it the constant R. And now it's just 22.4 divided by 273, or 0.0821 atmospheres, liters, Kelvin, moles. And so now we can rewrite our equation. Instead of this being Instead of this being that, we can rewrite it as R is equal to PV over NT. And because of the printing press restrictions at the time, they just rewrote it by rearranging the algebra into PV equals nRT, where R is what's called the ideal gas constant. And so now, in all of the other gas laws before this, we had to have a before condition and an after condition to be able to understand the properties of the gas as they would change. But with the ideal gas law, we can just measure the pressure once, or measure the temperature once, or measure the volume once, and the other conditions of the gas are apparent because of its relationship to the ideal gas condition. So, you are trying to build a spaceship, and you're like, okay, we want the spaceship to be 1 ATM all the time, and we would like the volume of the spaceship to be like 20,000 liters of gas. So the question is, okay, well, how much gas do we actually need to put in there if we want the temperature of the spaceship to always be about room temperature, 25 degrees C, so 298 Kelvin? Well, you can see now that we can solve for the amount of gas that we'll need in our spaceship without having to do any sort of before-after condition. If we want 1 atmosphere, 20,000 liters at 293 degrees Kelvin, then the amount of gas will just simply be 1 ATM times 20,000 liters all over R times the 298 Kelvin. So it looks like we can't solve this because we don't have R, but remember that R is the ideal gas constant, 0.0821 atmospheres, liters, Kelvin, moles. So now we can plug that in, and you'll notice atmospheres will cancel, liters will cancel, Kelvin will cancel, and the only thing that doesn't cancel is moles. And that will tell us the moles of gas that need to go into our spaceship. Pretty handy, especially when you're trying to design something like the International Space Station, and you're constantly having to send air up to the astronauts. You need to take these types of laws into consideration. Another thing that would be important is looking at the pressure swings that would occur in a spaceship that didn't have insulation in it. Say, for instance, you're making a satellite. Well, when a satellite is in the Earth's shadow, it's going to be negative 250 degrees Celsius. And when it's in the direct sunlight, it's going to be 250 degrees Celsius. So that 500 degrees Celsius swing is going to have a huge effect on any pressure and volume that is inside of that satellite. And so what are those pressures going to be? Well, PV equals nRT can show you those different pressure values at the different temperatures throughout the satellite's movement around the Earth. And then, of course, because this is moles, we can then convert this into our grams if we want to actually weigh it out. So if we plug in our numbers here, this would be 1 times 20,000 divided by 0.0821, and then times 298. This will give us our moles. So let's plug it in. Boop, 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 boop. So 20,000, because 1 times 20,000, we don't have to do that. And then we're going to divide that, and we got to use parentheses here, 0.0821, and then times that by 298. We have 817.5 moles of air. Air weighs about 30 grams per mole because it's mostly nitrogen and oxygen. So we can then convert this with the conversion factor. 1 mole of air is equal to about 30 grams. So then we just take our answer and multiply it by 30. So we're going to have to put 24,525 grams of air into our spaceship to be able to maintain this condition. That's a very small spaceship, by the way. You probably can't even fit in it. I think the International Space Station is probably close to like 2 million liters or something like that, but that was the idea. So those are the gas laws. Now, obviously, you can also use ideal gas law and Avogadro's law for what's called gas stoichiometry. We already did that in the previous unit when talking about simple problems where everything was a gas. We just said, okay, well, let's just assume everything is at STP. And so then we can just say, okay, even though the ratio is 2 to 2, then we can just simply call it liters. But now we can do it in, say, in case it wasn't a gas. Say we want to know how much hydrogen gas is going to be produced by throwing sodium in the water, because we're interested in the hydrogen gas to maybe sell, or because it's explosive and we're trying not to cause an explosion. And we're like, okay, I have a container and I want to fill my container completely up with hydrogen gas. And say, for instance, I have a 500-liter container. Well, what size of sodium, what gram size of sodium do I need to do that? So we can use the ideal gas law and gas stoichiometry to solve for this. So first, if it's stoichiometry, we need a balanced chemical equation. So we're going to need to put a 2 there and a 2 there. But then also, if we're going to solve for this, we need to know all the conditions. If it's an STP, we can simply solve it. So say it said at STP. Well, for that, we can just use the equivalence of the 22.4 liters. So we have this for every 22.4 liters of hydrogen, there's 1 mole of hydrogen. And then now we can just do the basic stoichiometry. For every 1 mole of hydrogen, there's 1 mole of sodium. And then we can just plug in the sodium to the 23 grams of sodium. And you can see that looks a lot like our stoichiometry from the previous unit. But say, for instance, we're not at STPs. Say we're at, for instance, room temperature. We're going outside to do this, and it's a particularly hot day. Say it's 313 Kelvin, and the pressure, since it's a hot day, the pressure is a little bit higher. Say we're at 1.1 ATM. So now what we would do is, instead of this step right here, what we're going to do is we're going to find N with using PV equals nRT. So in this case, we're going to solve for N. Our pressure is 1.1 ATM. Our volume is the 500 liters. Our R is 0.0821 atmospheres, liters, Kelvin, moles. And then our temperature is 313 Kelvin. So now this will give us the N that we multiplied by 23, which is going to be different than just dividing it by 22.4. So in the previous example, this is just 500 divided by 22.4 and then times 23 to give us 513.4 grams of sodium. But now in this example, we have 1.1 times 500 divided by 0.0821 times 313. So that gives us 21.4 moles of the hydrogen, or sorry, the hydrogen. And now we can do our stoichiometry. 1 mole of hydrogen to 1 mole of sodium. And then for every 1 mole of sodium, there's 23 grams. So because of this, we now multiply this by 23. We only need 492.3 grams of sodium. So if we didn't measure the temperature and the pressure of our system, and we tried to do this reaction, we would cause our container to explode if we used the STP values. We were using almost 20 grams more of sodium than we needed. And that hydrogen would have nowhere to go, and we might cause an explosion. So this is a good example of gas stoichiometry. There was another thing I wanted to show you. If R, remember, is equal to 1 ATM, 22.4 liters, all over 1 mole, and then we multiply that by 273 Kelvin. If that's R, Well, then aren't there multiple pressure measurements that we can use? And the answer is yes. So we can also have a 760 mmHg because everything else is the same. The only difference is that we measured our pressure in terms of millimeters of mercury. So all this is going to do is just multiply this by 760, which is 62.4 mmHg, liters, Kelvin, moles. And then what you might see a lot as the actual R value, I think your book uses this one, is 101.3 kilopascals, 22.4 liters, all over 1 mole, and then 273 Kelvin. Well, that gives you 8.31 kPa, liters, Kelvin, moles. And so sometimes they will call this the ideal gas constant. But remember, they're all the exact same thing. The only difference is which pressure measurement you use. Well, that's everything for chapter 14. That's the gas laws. So if you have any questions, let me know, and I can go over them. If not, that's it for today. Thanks, guys.